Hello everyone, it's my pleasure today to present you our paper UEyes, Understanding Visual Saliency Across User Interface Types. It is important for the HCI community to understand how people look at user interfaces. The fundamental question for HCI is in which way are UEyes special? How do they differ from natural things when people look at them? Answers to this question are valuable for designers. They already use visual saliency information to evaluate and improve their designs. Saliency maps are often useful in identifying visually salient areas of a user interface and can determine which parts of the interface are most likely to attract users' attention. Scan paths can provide designers with insights into visual flows so that they can adjust UI designs to encourage users to view UI elements in the desired order. In real-world scenarios, user interfaces can differ significantly based on the device and functionality. Consequently, the number of elements and how they are displayed can vary a lot across different user interfaces. For instance, web pages have a large number of images and text, while desktop UIs tend to feature small images. Mobile UIs typically have more components structured as widgets. How do such differences affect how users look at user interfaces? Understanding the ways in which users view and engage with different user interface types can provide insights into how to better design and optimize user interfaces for different devices and use cases. In this project, we first collected UEyes, a novel large-scale eye-tracking dataset captured by a high-fidelity in-lab eye tracker. Based on the collected data, we systematically compared user viewing behaviors and analyzed the dataset regarding different factors. We then further compared existing predictive models for saliency maps and scan paths on how well they perform across the UI types, and made improvements to existing models informed by our data. Most visual saliency datasets available today are often limited to a particular type of visual design, with relatively few saliency results collected from a small group of participants. For example, Leiva and his colleagues collected a mobile UI saliency dataset with 30 participants and 193 mobile UIs. To address this limitation, we collected a larger UI saliency dataset, including 62 participants and 1,980 UIs from 4 different UI types. Another highly relevant prior research is UMSI, which proposed a crowdsourced saliency dataset and a predictive model of saliency importance trained on images from different design classes. Although crowdsourcing approaches enable the collection of large eye-tracking datasets with proxies of eye-tracking data, such as cursor-based or web-based methods, they cannot simulate the same results as collected by actual eye trackers. Webcam-based approaches suffer from low accuracy, while cursor-based methods reflect different cognitive processes from eye movements. Unlike UMSI, we collected real-time eye-tracking dataset via a high-fidelity in-lab eye tracker for accurate results. In addition, our UEyes dataset includes both multi-duration saliency maps and scan paths. We presented the UI images on a desktop monitor. To mimic users' typical viewing experience, we used the same visual angle for all UI types to ensure a fair comparison. We analyzed the dataset regarding different factors, such as location bias, color bias, saccade angle and amplitude, and visited and revisited elements. For example, compared to the center bias of natural images, participants paid more attention to the upper left portion of the UEyes. However, different UI types have different location biases. For web pages, fixations are spread across the entire upper left region, while there are 2 bands of salient regions in desktop UEyes, one right above the center of the UI and the other near the upper left-hand corner. Existing models for saliency map prediction mostly only focused on continuous distribution of the saliency maps rather than on individual fixation points. In addition, they are mostly trained on crowdsourced eye-tracking dataset collected via cursor or webcam. So they cannot properly simulate the results captured via data from eye trackers. Thus, we added location-based loss terms during the training and trained on our UEyes dataset to predict more accurate results. Existing models for scan path prediction trained on natural things cannot easily adapt to user interfaces. We made some improvements to two state-of-the-art models to enable scan path prediction on UEyes. However, each model still has its own strengths and limitations after improvement. Typicase++ is better at predicting fixation points, as it is based on saliency maps that highlight elements on the UEyes. However, it can lead to unrealistic scan paths. On the other hand, PathScan++ excels at generating realistic trajectories thanks to its discriminative component in the network. However, it falls short in predicting fixation points, and the generated points are often outside the areas of interest. In summary, we collected UEyes, a large-scale eye-tracking dataset that covers 62 participants and 1,980 UEyes of 4 types, and includes both multi-iteration saliency maps and scan paths. Moreover, we presented the first in-depth analysis and comparison of eye movement tendencies across common UI types. We also contributed solid performance analysis of the existing and our improved predictive models for saliency maps and scan paths across the various UI types. Thank you.